Take a look at a modern industrial facility. Thousands of pipes, heavy machinery, and specialized process components operating continuously. Keeping this physical plant running requires a constant, highly coordinated flow of information. For reliability engineers, the core challenge is Enterprise Asset Management, or EAM, content development. Before a technician can turn a single wrench, engineers must define exactly how every piece of equipment should be maintained and analyzed over its lifecycle. This EAM content includes highly detailed preventative maintenance, or PM, routines. It requires precise diagnostic failure codes and comprehensive lists of compatible spare parts mapped to exact machines. Here is the operational bottleneck. A standard facility contains upwards of 10,000 unique physical assets. Attempting to build and assign distinct maintenance content for each of those assets, one at a time, is administratively impossible for any engineering team. Managing physical assets strictly as individual entities leads directly to operational paralysis. You cannot maintain thousands of machines if your data structure requires you to evaluate every single one from scratch. To understand why this fails, we have to look past the physical plant floor and examine the underlying digital database used to track these machines. This is an unstandardized facility database. We see 200 individual pumps with completely mismatched naming conventions, empty cells, and no logical grouping. This chaos happens when the database treats every asset as a unique, isolated data silo, causing the maintenance data to fragment. Systematic asset classification provides the mandatory architecture needed to resolve this. By grouping similar assets together according to shared characteristics, organizations can break EAM content development into discrete, manageable chunks. This classification transforms an unsearchable list of 10,000 random items into a unified, queryable system based on exact operational functions. We achieve this structure by building a strict top-down data hierarchy. Level 1 of the taxonomy is the equipment category, dividing the plant into high-level domains like rotating equipment and electrical. Level 2 is the equipment type, subdividing broad domains into major functional categories like pumps and compressors. Level 3 is the equipment class, grouping assets by specific operational features. Pumps separate into centrifugal, vacuum, or reciprocating configurations. There is a strict rule for Level 3. Classes must be mutually exclusive. Because a centrifugal pump operates differently than a vacuum pump, they must sit in distinct, non-overlapping classes to ensure the data remains clean. Finally, Level 4 contains the characteristics. This tier houses granular, asset-specific data points like power rating and exact model numbers. This 4-tier hierarchy acts as the structural blueprint dictating the maintenance strategy for every asset. To see how this classification creates precision, let's focus specifically on the centrifugal pump class. By defining this class, we identify the exact data attributes required to track it, including total head, net positive suction head, and impeller size. This exact set of data fields is mandatory for monitoring a centrifugal pump, yet it would be irrelevant for an electric motor. The class definition ensures the right data is collected for the right machine. Enforcing this attribute matrix ensures perfection in data entry. The individual fields snap together to automatically generate perfectly formatted, standardized asset descriptions. This structure removes the guesswork for technicians and data clerks. It eliminates typos and ensures no critical performance information is skipped during database entry. This structured data profile becomes the locked custom template for that specific asset class, guaranteeing data consistency before a single physical asset is even entered. This brings us back to the core challenge. How do engineers efficiently build maintenance plans for 200 individual pumps without doing the work twice? The solution is the one-to-many content multiplier strategy. Because all assets within a specific class share identical mechanical operations, the reliability engineer only needs to develop the preventative maintenance plan once at the class level. That single master plan then propagates downward, applying the correct maintenance routine to all 200 individual physical assets within that class at the same time. Standardized diagnostic data is inherited using this exact same multiplier. Problem, failure, and action codes are defined once at the class node and then shared by every machine in that group. This method creates a massive reduction in administrative overhead, turning months of repetitive data entry into a single high-leverage engineering task. This one-to-many approach allows an organization to address the data requirements of 10,000 assets by defining only 50 distinct class templates. Grouping assets into a class does not mean every machine in that class shares the same operational priority. Classification is simply the prerequisite step required before you can accurately determine criticality. To allocate resources effectively, you must first separate the high-pressure process safety valves from the facility doorknobs. This ensures resources are deployed where needed most. When beginning an EAM project, operations directors should focus their content development strictly on the specific classes that demonstrate the highest frequency of work orders. Classification provides a strategic map that tells maintenance teams exactly where to deploy their finite resources for the highest possible return on investment. Once the data architecture is standardized, the facility gains a new capability: the use of reliability analytics to drive decision-making. A critical metric for tracking this reliability is mean time between failures, or MTBF. Because failure codes are inherited and standardized through the classification hierarchy, it becomes possible to compare equipment performance accurately across the entire plant. This chart compares the mean time between failures of reciprocating pumps against centrifugal pumps. By running analytics at the class level, engineers can identify statistical trends in reliability and adjust their procurement or maintenance strategies accordingly. Rigorous reliability analytics and optimized spare parts management are only possible when a rigid classification schema serves as the foundation. Implementing this system in a real-world environment requires a specific deployment framework. Step 1 is defining your categories and classes from the top down. Step 2 is gathering the relevant master data attributes, like power ratings and manufacturers for those specific classes. Step 3 involves configuring your computerized maintenance management system to match this exact taxonomy, ensuring the software enforces the new data standards. Steps 4 and 5 involve training your operational team to use the structure correctly and conducting regular audits to prevent data decay as equipment is replaced over time. We return to the plant floor. Now every pipe and pump is part of an orderly digital system, rather than an anonymous piece of hardware. High-performance maintenance programs are built on the foundation of a rigorous master data architecture. Asset classification is the structural blueprint that transitions an organization from reactive maintenance chaos to scalable, predictive reliability.